Alright, here is your video lecture for Chapter 2, Section 3, entitled Using Scientific Measurements. Objectives for this section: distinguish between accuracy and precision. This is something we worked on in class already. Determine the number of significant figures in a measurement. Perform mathematical operations involving significant figures. Convert measurements into scientific notation, as well as distinguish between inversely and directly proportional relationships. Now, this video is going to be pretty long. I'm going to try to get through it pretty quick. However, there will be opportunities for you to practice, little checks for understanding. Please feel free to pause the video whenever you feel necessary to catch up on your notes or to give yourself time to do those practice problems. So let's remember, a measurement is any quantity that is measured, and in order for it to be a proper measurement, it needs to include both a number and a unit. Don't forget that, and so that you can get full credit on any problem in which you need to show your work. So we have 2.34 grams, 36.1 milliliters, 16.5 years old. All of these are numbers with units. What we're going to start working on here is how certain are you that your measurement is correct. And you'll notice I have a few digits underlined here, and we'll explain how we use these digits to determine how certain our measurement is. So first thing, distinguish between accuracy and precision. Accuracy is the measure of how close a measurement comes to the actual or true value of whatever is being measured, or proximity to a true value. Precision is a measure of how close a series of measurements are to one another, not necessarily to the true value, but to one another, which refers to your ability to be reproduced. Now we're going to use an example where we try to guess how old my dog is, and you're going to be thinking about whether or not you yourself were accurate, and compare your potential answer to the potential answer of your classmates. Again, accuracy closest to true value. Precision is your ability to be reproduced, or the measurements ability to be reproduced. Here we have the dartboard example again, where good accuracy, we're hitting the bullseye, and good precision, they're all grouped together. Here we have poor accuracy because we are not hitting the bullseye, but we have good precision because of the tight grouping. But then we have poor accuracy because we're not close to the bullseye, and poor precision because the grouping is poor. All right, so let's talk about error. Okay, so here's the example. We're going to look at my dog. Her name's Cora. She's a sweetie. Here she's laying on her Giants blanket. It's her favorite. I want you to take a guess about how old my dog is. Look at my dog. Take a guess how old she is. I want you to do it in months. Now, I do want you to make a guess. Do that now. Turns out she's 42 months old. All right, and we're going to use this value, 42 months, and whatever value you guessed in your own head to go through and talk about error and percent error. So error, I'm sure you're pretty familiar with this idea already. You take your experimental value, that's whatever you just measured, or in this case with Cora and her age, it's whatever you guessed was her age. That's the experimental value. And you're going to determine or calculate the difference between that experimental value and the accepted value, which is the true value that she's actually 42 months old. The error is the difference between those two values. So what is the error in your measurement of the age of my dog? Percent error, which is different than error. This is percent error. This gives you an understanding of how close you were to the accepted value in terms of percentage relative to the actual value you're comparing your error to. So the percent error is always an absolute value, which means it's always positive, never negative. That's what these bars right here, let's get my laser pointer. That's what these bars on the side of the experimental value minus accepted value over accepted value are. These are the absolute value notation. We're going to multiply by 100% so it can be reported as a percentage. So what is the percent error in your measurement of my dog? So let's throw some numbers in there. let's say, for example, you guessed that Cora was 60 months old, okay, and she's a lady, so that's probably a bad idea for you to guess high, right? You want to guess young. But anywho, let's assume that you guessed 60 months. Now, the actual value is 42 months. She's actually 42 months old. Error is experimental value minus accepted value. So that would be 60 months minus 42 months. So your error would be 18 months. You're 18 months off. Percent error, we're going to take the same error, right? The same equation for error, but we are going to divide that by the accepted value, 42 months, and we'll multiply by 100%. Okay, it's going to turn into a percentage of 42.9. That's a pretty high percent error. And so what that means is you weren't that close, right? You might think like, oh, I wasn't off by that much. I was only off by 18 months. Well, compared to her actual age of 42, 18 months is a pretty big chunk of her life. All right, you're 42.9% off. That's a pretty large percent error. Let's move on to determining the number of significant figures in a measurement. Significant figures, sometimes referred to as significant digits, depending on just how you learned it, will be shortened to sig figs or sig digs, just for short. It's a measurement, and those measurements, the significant figures of a measurement, include all the known digits plus one final digit that is an estimate. Yeah, and the reason that significant figures are important is because they allow us to communicate how precise our measurement is and the certainty of our measurement. That's important because, say, you're buying something that's really, really expensive. I don't know, $1 million per centimeter. How precise do you want that measurement to be? Do you want to be off by a little bit or a lot? You don't want to be off by nothing, right? You want to be very precise in your measurement, very certain, very confident in your measurement. So significant figures allow you to communicate how certain you are. Moving on, talking about significant figures and how they relate to certainty. Look at this situation right here. I have a piece of wood, and I'm not exactly sure how long it is. I have a meter stick, okay, and it doesn't have any notches to tell me centimeters or millimeters. But it's a meter stick. I can tell that my block of wood is a little bit beyond halfway. It's halfway past my meter stick, but not all the way to about 3/4. So I'm going to estimate it's about 0.6. So 0.6 meters. I'm using one significant figure. I don't have any known digits, and the 0.6 is my estimate. Moving on to the next example. We have a meter stick, but now we have the indication of centimeters. So here's 60 centimeters and 70 centimeters. I know for sure I'm in the 60s. Okay, I can tell for sure using these notches that I'm in the 60s. Now I know that I'm not in 70. I know I'm above 60, but I don't know 61, 62. That's too much. So I'm going to use one certain figure. I know I'm in the 60s. This one right here is not one I'm quite as confident about. It's an estimate. It's an estimate. So here I have two significant figures. The one in the 100th place is the estimate. Moving on, here we have a meter stick with millimeter indications. So now I know for sure that we're in the 0.6 meters range. I can now see, because of this millimeter bar, that I'm not quite to 0.61. I'm actually less than that. I'm actually going to estimate 0.609. So here I have three significant figures, the 6 and the 0 being certain, the 9 being an estimate. So which measurement has the most certainty and the greatest precision? The last one, the most significant figures. And that's what I'm wanting you to see. More significant figures equals more precision, more certainty. So when you look at a measurement, you're going to need to determine how many significant figures are in that value. There are a few rules you're going to have to know, need to take down, and you will want to be writing these down as we go, as we establish the rules. And I'm going to try to give you a moment to try to figure out the rules on your own. And the way I'm going to do that is on the next few slides. As I advance, I'm going to tell you how many significant figures are in each of these values on the left. I'll reveal how many significant figures are in this value, and then this value, and then this value, and then this value. After that, we'll try to formulate our rule for establishing the significance of a figure. All right, first value, 4 significant figures. Second value, 2 significant figures. Third value, 3 significant figures. Fourth value, 5 significant figures. Take a moment, drink that in. Let's move on and try to complete this rule. So I have this statement, all non-zero digits in a measured number, right? None of these are zeros. They're all non-zeros. All non-zero digits in a measured number are, well, they're either significant or not significant. So we need to figure out which one. Okay? Take into account how many significant figures I've identified, all of the non-zero digits here. We can complete this sentence by identifying significant. All non-zero digits in a measured number are significant, and that is your rule for non-zero digits. Let's move on to rules about leading zeros. Notice that there are zeros in front of the first non-zero digit. That makes it leading. It's a leading zero. Okay, we have 3 leading zeros here. We have 4 leading zeros here. So they're leading zeros, and this is what we're going to talk about here. All right, first value. That's 1 significant figure. Second value, 3 significant figures. Third value, 2 significant figures. Fourth value, 3 significant figures. So we want to complete this rule. All leading zeros in numbers are, I hope you guessed, not significant. Okay, notice none of these zeros in front of the number are being counted toward the number of significant figures. Now, sandwiched zeros. Notice we have this 0 in between 2 non-zero digits, in between the 5 and the 8. There's 1 sandwich in here. We have 2 sandwiched zeros in between the 2 and the 1 in this value. There's 1 sandwiched 0 here and 1 sandwiched 0 here. Notice these are zeros, but again, these are leading zeros. These are leading zeros, and we just established that those are never significant. So first value, 3 significant figures. Fourth value, 4 significant figures. Third value, 3 significant figures. Fourth value, 3 significant figures. So help me complete this rule. All zeros in between non-zero digits are significant. Okay, so leading zeros are not significant. Sandwiched zeros are significant. All right, we're going to talk about trailing zeros, and this is where most students get a little confused. All right, there are 2 different kinds of trailing zeros. There are trailing zeros in numbers with decimals, and then there are trailing zeros in numbers without decimals. Notice here we have values that have no decimals present. There's no decimal here. So our rule is going to pertain to trailing zeros without decimals. All right. First value here, 2 significant figures. Second value, 1 significant figure. Third value, 3 significant figures. Fourth value, 5 significant figures. So help me complete my rule. Trailing zeros in numbers with no decimal are not significant. Notice all these trailing zeros did not count towards the number of significant figures. 1, 2 non-zero digits are the only significant figures here. There's only 1 significant figure in 200. It's simply the non-zero digit. So trailing zeros in numbers with no decimal are not significant. Now let's talk about trailing zeros in numbers with decimals. Notice that we have decimals here. So this is what you want to find. Even at the end, there's a decimal there. That's going to change your rule. So first value, 4 significant figures. Second value, 5 significant figures. Third value, 6 significant figures. Fourth value, 8 significant figures. Okay, notice that this 25,005,000 was present in the previous slide. However, on the previous slide, no decimal was present. On this slide, the decimal is present, and that changes the number of significant figures. So help me complete this rule. Trailing zeros in numbers with a decimal are significant. All right, take an opportunity to pause the video so you can try this on your own, and then I'll give you the answers. For A, options 1 and 3 are correct. For B, options 2 and 3 are correct. And for C, options 1 and 2 are correct. Hope you got those right. If you didn't, go back and review your rules and try them again. All right, here's another check for understanding. Pause the video so you can have an opportunity to think this through, and then I'll give you the answer. All right, so the set that has the same number of significant figures, option 3. They both have 2 significant figures. Pause the video so you can have an opportunity to complete this check for understanding. A has 2 significant figures, B has 4 significant figures, C has 1 significant figure, D has 3 significant figures, and E has 3 significant figures. Take a moment to pause and generate an answer to this check for understanding. So if you want to report 7,000 centimeters with 1 significant figure, you're going to include a 7 and no decimals, right? Trailing zeros and numbers with no decimals, not significant, so that there's 1 significant figure present there. For B, they want 5 significant figures. How do I do that? I add a decimal and then an extra trailing 0. I know with more certainty that is 7,000 centimeters. Similarly, for 6 significant figures, you'll add yet another trailing 0 behind a decimal. Moving on, we need to be able to perform mathematical functions involving significant figures. So a calculated answer cannot be more precise than the measuring tool used to generate the measurement in the calculation. All right? A calculated answer must match the least precise measurement. The least precise measurement. Similarly, that old axiom, chain is only as strong as its weakest link. A calculation is only as certain as its least precise measurement. Okay. Now there are 2 different sets of rules here when doing calculations. There's rules for significant figures if you're doing adding and subtracting, and then there's a different set of rules for if you're doing multiplication or division. Rules for addition and subtraction. The answer has the same number of decimal places as the measurement with the fewest decimal places. Here we go. We have 25.2 has 1 decimal place. 1.34, 2 decimal places. Now, if you were to put this into your calculator, you'd generate 26.54. However, that's not the correct answer. Your answer can only be reported with the same number of decimal places as the measurement with the fewest decimal places, which is the 25.2, 1 decimal place. So your answer needs to be reported in 1 decimal place. So you're going to have to round to this first decimal place. So the answer you're going to report is going to be 26.5. All right, take that into consideration and press pause on the video to attempt this check for understanding. All right, I hope you selected option 2 and option 3 for B. If you didn't, go back and check your rules and try them again. Now here are your rules for multiplying and dividing. You're going to round or add zeros to a calculated answer until you have the same number of significant figures as the measurement with the fewest significant figures. So we're not worried about the decimal place here. When we're multiplying and dividing, we worry about how many significant figures are present. All right. So pause the video and see if you can use that rule to select the correct answer for each of the following checks for understanding. All right, I hope you selected option 2. Okay, notice 2 significant figures versus 3 significant figures. We have to use the fewest number of significant figures. So even though you are going to put this into your calculator and you're going to generate 9.198 as your response, you can only know the answer to this second significant figure. So you're going to have to round to 9.2. For B, I hope you selected 3. There's only 1 significant figure here. For C, I hope you selected 2. There are only 2 significant figures in both of these values here. All right, we're going to check for understanding again. Go ahead and pause the video and see how we're doing. All right, I'll walk you through the first one of 7.55 meters times 0.34 meters. Okay. Now, if we were to simply plug this into our calculator, we would generate 2.567. But I want you to notice, we're multiplying by 0.34. 0.34 only has two significant figures. Therefore, your answer can only have two significant figures. So I'm going to have to round to this spot right here. So my answer to report and get full credit is going to be 2.6 meters. Your answer for B, I hope you got 1.5. And then your answer for C, I hope you got 0.29 meters. There's one more. Calculate the volume of warehouse that has inside dimensions of 22.4 meters by 11.3 meters by 5.2 meters. So again, we multiply these three values and you generate in your calculator 1,316.224 meters. However, that does not reflect the certainty of these measurements. Okay, they don't have the proper number of significant figures. We need to find the value within the problem with the fewest significant figures, and I see them here. Okay, 5.2. That only has two significant figures. So that's how many significant figures your answer must have. In this case, that's 2. So the way you're going to report your answer is 1,300 meters. Now, let's talk about something a little bit different. I have 2 dogs. 2 dogs. How many significant figures are present in the statement 2 dogs? It's not one significant figure. It's actually an unlimited significant figures. Note, any number that is counted as an exact number has unlimited significant figures. There is no estimated number. All right, so here I want to draw the difference between exact numbers and measured numbers. Okay, exact numbers are used in definitions. Right, 1 dozen eggs are defined as 12 eggs. Right, not 11.9 or 12.1. It's always 12. Exactly 12. Exactly 12. So it's assumed to have an infinite number of significant figures. Here, I have 2 dogs, therefore I have an infinite number of significant figures. Because significant figures are based on an estimated digit, which I don't have here. I know exactly how many dogs I have. It is 2. Similarly, I had 8 students attend AST yesterday. How many significant figures do I have? Unlimited. Okay, unlimited. 8 students showed up. So, excuse me. When you're using an exact number, okay, that's an unlimited number of significant figures. If you're using a measured number, you're going to have to include some sort of estimation at some point, and so you'll have a specific number of significant figures. We need to be able to convert measurements into scientific notation. What is scientific notation? It's simply a quick way to write really, really big numbers or really, really small numbers. So the different rules for scientific notation, you need to be able to put that number